hit go live. So when I hit go live, I have to like wait for a minute to make sure it's live. Sometimes there's like a issue that happens and it doesn't go live. And doing that while like I'm looking around this screen like a complete idiot. And I'm surprised someday someone will comment, why is this guy looking in all directions?
Yeah, it's fine, no worries.
Awesome, we are live. I can hear myself speak, which means we are live. I'll quickly share my screen and get started. Hey everybody, thank you for joining us on a Saturday afternoon, evening, or morning, depending on wherever the world you're joining us from. I'm super excited to be hosting GIlles today. We'll be learning about their team's first position first. So this is not just gold. This is not somewhere in the upper portion of the leaderboard. This is the top of the leaderboard. And this is CTDS 2.0. So I'm super excited to host GIlles. GIlles, thanks for joining me today.
Thank you so much for having me, Sanyam. It's an honor to be here.
I'm super excited and can't wait to dive into your journey. I'll quickly give the audience an outline of what we're talking about and then start by asking you about your journey.
Sure thing.
So a quick reminder to everybody joining us on YouTube, here's the link to ask any questions. If I head over to this link, it should take you to our forums. And you can ask any question here as a reply, and I'll keep an eye out for any questions. So please keep the questions coming on here, and we'll keep checking from time to time. I'll post this link in the YouTube chat real quick so that everyone can ask questions here. Awesome. I think I just saw a message from one of your teammates who's also there in the chat. So that's awesome to see. Thanks for joining us.
Whoever's there, because I can't see it, welcome, and thank you for being here to my teammates.
Awesome. Now that the logistical stuff is out of the way, I'll take another boring minute to explain why is this happening. This is Chai Time Data Science 2.0, and essentially it's a version 2 of what I've been doing for a long time, where I also learn about the guest journey and also understand their solution walkthrough. I really believe, and to anyone who spent any time on Kaggle would know, that whenever you go through a solution in depth, you learn so much. And that's why I try to reach out to awesome people like GIlles himself and try to learn from their not just their journey, but also their solution. So that's what we'll be doing today. A very small intro to GIlles. I know it's not enough, because you can see on his Kaggle profile here, there are 4 gold medals, 3 silver medals, and 2 bronze medals. These are incredibly hard, and I suppose if GIlles ever comes back on the show, he should be a grandmaster by then. Currently, he's a Kaggle competition master and a postdoc researcher at Kent University. You can find him on Twitter at GIlles VDWIELE. So please make sure to check his profile there. So I'll stop sharing my screen and now go back to the classical model. Thanks again for joining me. I would love to start by asking about, how did you discover the world of machine learning, and how did you get started on Kaggle?
Yeah, so I think they actually quite coincide very well, because I got introduced to both machine learning and Kaggle during a course at university. It was in my first master's, I believe. And that was basically the first time I ever got to experience what machine learning actually is. I did have like some courses on statistics, but those were not really machine learning oriented, I would say. And so one of these things within these courses is a project, and that is hosted on Kaggle. So during my year, we had to like recognize traffic signs. So Belgian traffic signs, we have a whole bunch of them on the Belgian roads, and we were given images. And so we had to say which of the 60, I believe, traffic signs were in that image. I didn't do that well, I remember as well, on that first competition. Probably top 60% or something, but I was hooked straight away. The competitive drive that I typically have really aligned well with how Kaggle works, and it was also just a great learning experience. So that's how I got introduced to Kaggle.
And this was during your master's?
Yes, so that was during my first master. So now I would have to calculate how much back in time that is. It probably is 2015, 2016, somewhere around that. So it's 5 to 6 years ago that I made my first steps on Kaggle, I would say.
So you've followed the traditional path in academia, if I may, wherein you signed up for a bachelor's, a master's, and a PhD. People assume this is very disconnected from competitiveness. How did you find the world of Kaggle as compared to the academic life? And how did you improve on Kaggle once you signed up?
That's true. That's actually, yeah. Well, maybe there is some competitiveness in the academic world, I would say as well. Like people, like for example, in the deep learning community, people are continuously improving just fundamental research, and they typically do it on these benchmark data sets. MNIST being the most typical one with its many flaws though. But people, just work on those data sets. And so their goal is to improve the scores that are published as of today. So you can somewhat draw an analogy with the Kaggle leaderboards there. On the other hand, there everyone is setting up their own evaluation, while Kaggle has a standardized fixed evaluation procedure for all of the models. So that makes it a bit of a more fair comparison, I would say. But so I think they align well. So the competitive aspect of Kaggle can work pretty well with within academics as well, I would say. Many of the competitors and organizers on Kaggle are often academics as well. Like the research category of competitions are mostly organized by universities as well. So I don't think it's a complete mismatch.
That makes sense. And we were just talking offline about conferences, and I know, like, even I know just from talking to people, I'm underqualified to speak about it at all, just to get a disclaimer. But I know, like, this such a competitiveness. The CVPR deadline just passed, and it's so much work that many people, maybe I'm the only one, but many people don't realize how much competitiveness is also there in just research.
Yeah, it's mad. Like getting a paper on the main track in NIPS is probably at least as difficult as getting a gold medal on Kaggle, I would say. The acceptance rate is like only, I don't know by heart, but it is a low number, like 10 to 20%, probably something like that. And just the amount of effort that you have to put in a paper just to make like a small chance on actually being able to present it is indeed somewhat demotivating. But then again, if you ever are able to publish on this main track, that is really a prestigious achievement, I would say. And that's what makes it a bit more nice to chase. If it was too easy, then it probably wouldn't have been as prestigious as it is today. And there are also like, you don't per se have to submit to these main tracks. There are often like workshops which are more tailored towards a very specific subdomain, and there the acceptance rates are typically a lot higher. So that's a great starting point if you're interested, or a starting academic, to like go to conferences as well. Just try to submit to these workshops, and like that you can secure a spot in the conference as well and have a good discussion that week.
The acceptance rate sounds like sounds easier than getting a gold medal, just to say something spicy. Coming back to Kaggle, after starting your journey, how did you improve on your positions? You've had great achievements, both solo and both with teams. How did you approach Kaggle? How did you improve as a conscious effort?
Yeah, that's a good question. Because actually, after that machine learning project, my activity on Kaggle was quite low. I think I only participated like in one competition every 16 months, so not even on an annual basis, I would say. And I think that was probably because I was too competitive. And that would be a piece of advice that I would always give to people today, is to not focus too much on those ranks on the leaderboard. You should go for it for the learning experience in the first place. And whatever your rank is subordinal to just the learning experience that you'll get. And so that is actually what pushed me kind of away, because I wanted to do really, really well in all of the competitions that I participated in. And I still do, but so that's why I did put it a bit on the downside for some years. But then I think it was 3 years ago, I I don't know which competition it exactly was, but that's when I started to compete on a more active basis. I think it was together with the career competition back in that day. And I managed to obtain like the 6th place on the leaderboard there as well. It was just a playground competition, so there were no real medals. And that's very useful. Thank you. So indeed, I think like you can see, the traffic sign recognition was like the machine learning project, but then the Don't Overfit 2 and career competition, I participated in those two in parallel 3 years ago. And I think from that moment on, you can basically say that I was involved in one competition at each point in time. I did have like a few breaks of a few months in between, especially like in these competitions where I went all in and spent days and nights coding. Then I do kind of need to take a break after that. So that's where I have some small breaks. But other than that, I try to always be involved in one competition. That's also something I focus at, just participating in one, because I can't divide my attention to multiple competitions. That's just not how I work. Some people definitely work better like that, but I focus on one competition at a time. And then in terms of which one to pick, well, then I think you typically have like, to draw an analogy with reinforcement learning, the explore versus exploit trade-off, right? You can go for the competitions that you know that you're familiar with the data format, for example. So for my case, that would be time series competitions. That's where many of my gold medals come from. But on the other hand, I'm still on Kaggle to learn. And for example, when it comes to deep learning, I'm far from an expert in it. And so that's why I try to once in a while participate in like just a real computer vision or natural language processing competition. But then again, yeah, I do kind of switch between the exploit and the explore parts.
So you've recently graduated from your PhD as well. How does experimentation in a research setting compare against Kaggle? Do you see similarities? Because people complain there's not an overlap. I'm sure you would agree there's a nice overlap. Do you think there's a difference? Do you see any similarities?
Yeah, so in rough terms, they are kind of the same, but the optimizations you do on Kaggle are much more detailed than what you would do in research. Like hyperparameter tuning, for instance, is something we won't quickly do in academic research. We're having a new fundamental idea of this kind of modification to what is already out there, and we just want to kind of test that in isolation. While on Kaggle, you will go for any micro percentage that you can get from it, right? So you'll be tuning a lot more. So like the hyperparameters, feature selection, all that kind of stuff. But yeah, then in terms of how to manage these experiments, it's the same, right? So you have to keep like a structured overview of what have I done and what did I not yet do, or what are promising avenues that I should further pursue. So yeah, both in academics and Kaggle it's the same. While in the academic world, I would put my experiments on some server here at the university and let it run. On Kaggle, I'll put it in some notebook or in a Colab notebook, and I'll let it run just like that. And then back when the experimentations are done, I try to take note of it. I should do this in a more structured manner. So I'm a bit of a chaotic person. So most of my notes I've taken in my head. So I just try to remember all of the things I did and which things worked well and which things didn't work well. But once you start being involved in multiple projects at the same time, that's when you start realizing like, I can't keep track of this in my head anymore. And so it's something I'm trying to improve myself on, like having a more structured overview. And that's probably where tools like weights and biases come into play. They're perfect for these tracking of experimentations.
Yeah, thanks for the shout out. Even though this is on the weights and biases channel, we don't try to push too much about weights and biases, but happy to hear your feedback on it. So coming to the competition, I'd love to start diving into what the problem statement was about. But even before that, what made you sign up for this? This was a time series problem of sorts, as I understood. Why did you sign up? How did you decide to team up? Because usually for the audience, Kaggle competitions last from 3 sometimes to 6 months in rare cases. This was a 1-month competition. When did you team up with people? How did you team up? I'd love to know the story as well.
Yeah, so exactly. You already mentioned two of the key properties as to why I joined. The first one, it was a time series competition, and the data was temporal. So I'm quite familiar with that kind of data. But then the fact that it only lasted for 1 month is something I prefer than to 3 months, actually. Especially when you want to start at the start of the competitions. 3 months can feel rather long. You can be like a little bit burned out on that specific problem in the last 2 weeks of the competition. And so I also think one of my strengths is that I'm able to prototype and experiment rather quickly. While in these 3 months competitions, the details really start to matter. The winners will have everything perfectly optimized within the pipeline, right? While in those one month competitions, you can cut some corners because no one will be able to produce like a full-blown solution by the end of the month. And so that's why I try to choose those as well. Now, how did I get into this specific one? Well, I was rolled into it because I just got an email from Ka, who was a teammate of mine in the Liverpool competition and also the Halide competition, where we both got gold. And so he contacted me and Eve, who is called Sydney on Kaggle. And he said, yeah, like there's this interesting problem. Would you be interested in teaming up? And so at that time, I was still busy in real life, but Eve and Ka already started working on the problem. And I was like, I will join up with you guys in like 2 weeks. I first need to take care of some stuff. And so, yeah, 2 weeks later, I joined them and they already made some nice progress and had some nice insights. And from there on, us three continued, but we quickly noticed that we weren't gonna get the gold because our deep learning experiences was somewhat lacking, and this was clearly a deep learning competition. And so first we messaged Shuyun, who joined us, and he had like but I'll go more in depth on the solution, but he had a nice deep learning architecture up and running. And somewhat later we also messaged B, or Ricardo, to join us, and he joined us as well. And so like the blend, or just the simple combination of us five already gave us a high spot, and then in the end us five really cracked the puzzle, but I'll go into that later.
It was B in the chat. Now I couldn't understand who they were because they gave me the acronym, but now I know.
All right, hey B.
I'm sorry, I have had a power cut, so my monitor is off right now. I just need a minute to turn my laptop around. My webcam's
Sure.
on, but my laptop is gone, and I didn't want to interrupt you. So people now know that this is live, and I'm trying to fix this issue live.
Yeah, sure, no worries.
Awesome. So I'll have to probably look down now. My webcam's up there, and I'll be looking at my laptop screen. So Jill, I'm sorry, it'll look a little
No worries.
off to you, but I'm trying to fix this issue. I didn't know my monitor isn't on power backup. My PC is, but my monitor isn't. Just one moment. Oh, power's back. Sorry. Now I don't have to worry. I'll just put this back. Sorry about that.
No problem.
This was partly the reason why I was always so terrified to do Chai Time live, because of these issues.
Technical issues, yeah.
And I'm sorry. The first time this happened was during an interview with you. Sorry about that.
No worries at all.
Awesome. So I'm sharing my screen on the Ventilator homepage, and I'd love to. So for this part, Jill, I'll probably take the lead and just walk everyone through the solution as an outsider, just about the data set and everything. Please interrupt me anytime you feel I'm glancing over any details.
Okay.
So as I did a lot of Googling around this stuff, and I hope no one knows as much about ventilators because they're quite a serious thing, but from what I understood, these are used to provide help to people who can't breathe naturally. They're in such a position that they need help from a machine. And that's why this is being provided to them. The goal was here to simulate a ventilator, and the target was to reduce the cost barrier of developing methods. So quite literally, there was human life somewhat related to this competition. The evaluation criteria is, I don't need to go into this. It was mean absolute error. So just the difference and taking the absolute value, which means it can't be negative. You just turn it into a positive number, and you'd have to submit the ID and pressure variable here. What I've done here is I've shamelessly, no one would want to watch my EDA stuff. So I've used the famous ones here. This one gives a good outline of how a ventilator works. This is called Ventilator Pressure / LSTM starter kernel. And inside of a ventilator, there are two different parts, as I understood. There's an inspiratory and expiratory. This would come up in the data set also as UN and U out. Different things happen inside of it, and these connect to your lung like so. So you pass the air into the inspiratory, that goes to your lung, and you expire the air out to the environment. Shamelessly stealing from Ishan through his kernel ventilator EDA, I'll point out what columns were there in the data set. So the following, and this is from what, in my experience, I know it's a really tough competition, but the data was really simple to wrap my head around. So I'll rush through it. You had the ID across the entire file, and each breadth was given a unique ID. For every time step, there was a different ID. R measures how restricted the airway in the lung was. As I Googled, I found this is one of the standard metrics, so shouldn't be too surprising if you're familiar to the field. C indicates how compliant the lung is in, again, one of the standard metrics. You get the timestamp, and if you remember the diagram I just shared, UN measures the control input, and U out measures the control input for the exploratory solenoid valve, which is basically when you're expiring air. And pressure measures how much airway pressure is happening in the circuit. Did I miss anything here, Jill?
No, just like to draw an analogy, like R is for resistance and C is for capacity. So you can see or draw an analogy with like electric circuits, like resistors and capacitors. And that's what the semantics are for these lung properties. Yeah.
Awesome. So continuing further, Ishan has plotted some really nice graphs, and I'll probably just shamelessly use these to explain the analogy. This plots R against density. What was R?
Resistance.
Yep. As you can tell, I've not computed. I've just read through solutions, which is I'm blanking out through different portions. And this looks like an equal distribution across these values to me.
3 unique values indeed, 10, 20, and 50.
Mm-hmm. For compliance, it's the same case. These would be similar because if we looked at the definition, the scale was similar as well. And that's why for people who are not experts at Kaggling, you'd want to spend time in the data because you'd want to understand if it's not standardly distributed, or if some values are missing, or if there's, let's say every single R value was, let's say you had 99% values around 10, you'd just replace everything with 10 and just skip the column. So that's one of the stupid ways of dealing with it. Just letting everyone know. For UN, it was just around these two values, as I understood. And this is because input can't be of a very high density, as I understood. So that's why it will stay around these values.
Yeah, so this UN is basically, it's a percentage. How much is the valve opened? So from 0 to 100%, it can be opened. And maybe one little detail is that there's also like a very, very small bump at 100 as well in this distribution plot. And so they were also clipped, these values at 0 and 100. Like on the right, on the x-axis, you see a small bump in the density as well. And so that's because of the clipping that they did.
Yeah, but one of the fascinating things is I'm like a total outsider to all of these things. And now that like I've spent not as much time as you, but probably 10, 20 hours understanding this, I know much more about ventilators and all of this jargon that I'm able to wrap my head around this. And that's one thing that Kaggle also teaches you, I feel.
For sure.
So for the output, outputs control input. This means whenever you're exhaling it, there's also a factor that goes into the ventilator. The density basically revolves around two different values. And if you were to plot the timestamps, there was also an overlap with the different inputs going in, because probably the breaths weren't in sync with the patient, as I understood.
Yeah.
Okay, continuing further, pressure versus density had a spike around, I think this would be 5, maybe?
Yes, something like that, 5 to 6. That would be like the typical first value of your breath as well. But yeah, those are all details, but it's somewhere around that, the mode.
Thanks for confirming that. And quickly looking at different distributions across test and train, it looks like there was a quite similar distribution. So there no shakeup would have been expected from this competition of sorts. Awesome. I think these were the values I wanted to cover for the EDA bit. Anything I missed, Jill, or anything you'd like to add?
No, I think it was a great introduction. And I also have like in my slides that coming up in a bit, another way of looking at like a typical data sample, and that might make it a bit clearer as well. But I think this was great to introduce the problem.
Thank you. Let me see if there are any questions so far by the audience. No, I don't see any questions. Awesome. I'll probably point one more thing out before handing it to you. So why are we, if you're just joining us, why are we learning from Jill? Because first of all, he's a Kaggle master and he has amazing achievements. If you go to this competition, you don't even have to scroll. You can find their team right up on the top. And I'd also love to point out that there's such a huge gap between the first and second position, because they had this really innovative idea that we'll just learn about. So with that, I'd like to hand it back to you, Jill.
Okay, let me see if I can share my screen. Is it visible?
I can see the architecture slide.
All right, yeah, that wasn't the first slide, so a bit of a spoiler ahead already, but yeah, no worries. So I'll first quickly sketch the context, because I will be zooming in mostly on one part of our solution, the part that I was actually to give us that gap that Sanyam just discussed to the other competitors. But first, let me start off this talk, or this small part of the talk, with first acknowledging my teammates. So this victory would not have been possible without them. So here's an overview of them. And as you can see, we were kind of scattered all around the world. We had someone from the US, someone from Australia, and then 3 Europeans working around the clock on this competition, as to say. And maybe let's quickly look at how does one specific data sample look like. This plot basically visualizes all of the important properties of a single breath. So many of them were covered in the EDA we just went through. So as you can see, this breath was recorded in the lung with a certain resistance of 20 and a capacity of 50. And then the breath, so we are working on breath levels. We have about 50,000 breaths in the test set and 70,000 breaths in the train set to train our models on. And so each breath first consists of an inspiratory phase and is followed by an expiratory phase. And our models were only evaluated on the inspiratory part. And so typically this inspiratory part is around 1 second or 30 time steps long. There was a bit of variation on that. It could be 28 to 35, but the mean was around 30. And so the remaining 50-ish values were expiratory and were actually not even scored. But many of the models, or it was clear from the public notebooks, these expiratory values were very important to predict the inspiratory values, which is quite remarkable. Like, how could something from the future in a physical process be indicative of this present value? And it was kind of a slight hint towards what we found indeed. And so the blue one is the one we're going to be focusing on. You can see it as a one-dimensional problem almost. So we want to map this blue line to the green line as accurately as possible in this competition.
So because we're trying to predict the pressure based on the input values, that's why that's what we're aiming for, correct?
Correctly. So indeed, we want to use the UN values to predict what the pressure will be in the lung at any point in time. And so as soon as this orange function steps to 1, we no longer interested in our predictions. They can be as faulty as we want because it's not scored anyway. So
makes
this summarizes a sample. So we have 70,000 of these plots.
Yeah.
That's what we are working on.
Also, sorry, this is like a side
Sure.
note here, but I wonder if you've gone down the rabbit hole so much where I was like also reading through papers that show how you inhale and exhale. And I was like mentally trying to check if my patterns are the similar. So just like geeking out over how much Kaggle teaches you outside of just deep learning.
Exactly.
Also.
Yeah, definitely. Rabbit holes is what you are chasing often on Kaggle, and you can learn a lot from chasing those rabbit holes. That's for sure. But I didn't pursue that one specifically, but we chase many rabbit holes here in this one for sure. And then maybe very briefly on our deep learning architecture. So we used 2 architectures, and there kudos go to my team members Shuyun and B or Ricardo. So on the left, we have probably the most complex architecture, I would say. And the one on the right is just a very simplification of the one on the left. But the one on the left basically consists of a few LSTM layers, which is on the left block. And we also added some skip connections to it and an extra feed forward layer. And so we had 4 of these, if I'm not mistaken, but this was a hyperparameter, let's call it NL in this case. And then the representations learned by this part were further given to like a transformer encoder consisting of some 1D convolutions. Again, these skip connections were added to each of the layers. And so this model on the left did leverage features. So when we added features to our input, then we did notice quite some improvements. And so we did chase feature engineering or pursue feature engineering a lot during this competition. But more towards the end, Ricardo joined us and he had the model on the right. And surprisingly, this model on the right worked a lot better. No, not a lot better, but it worked better on the leaderboard than the one on the left. Maybe one side note is that the one on the left converged a lot quicker than the one on the right.
I'm sorry, so the main difference is that the one on the right is just being fed the raw data, and apart from that, the architecture is the same.
Exactly, and the architecture is much more simple as well. So we don't have these skip connections, we don't have a transformer part, we just have some stacked LSTM layers. So I cut everything away from the architectures except from the LSTM block. That makes it a bit confusing. This should just go an arrow from this by LSTM block to the output pressure, because that's how it kind of worked. So it was raw data, 4 LSTM layers, and then a whole lot of epochs on the raw data. And it also required some, how do you say it? Special learning rate schedules, I would say. So that was the thing or the breakthrough as to why this specific network converged. So B had some cosine annealing in there, and it was with a very low learning rate, I believe. And that's how he made it to converge really well on the leaderboard. And so a note, these 2 architectures, if you train them over multiple folds, let's say 15 to 20 fold cross validation, and you do that multiple times as well, just with different seeds, then you would end up with a whole bunch of models. For every fold and every seed, you would have a model. And so we have these 2 architectures. And so a blend of about 60 of these models would, I can't say with certainty if it would obtain you a gold medal, but it would be on the edge of getting it. So it would be top 25 for sure.
I'm sorry, sorry to keep interrupting you, but
no
I also love to understand how do you arrive at such architectures, because we see research papers and we know they're through like experiments. So to me, I'll just speak out my thoughts and please correct me. LSTMs are helpful because this is a time series problem and LSTMs are quite good at that. Let's say the FFN from there helps connect the layers. The skip connection is useful in missing out in connecting the transformer from there, or any details that the LSTM would encode to something else. I know it's just numbers, but I'm trying to get the intuition here.
Yeah, sure. Yeah, it's indeed like that. So the skip connections help a lot with convergence. And so the reason why LSTMs are so useful here is because of their long-term memory. So they are able to remember information from very early in the signal. And because they were bidirectional, they're also able to carry over information from the entire end of the breath as well. So that turned out to be very important. So information from the expiratory phase could really predict the inspiratory phase well. And that is just because of the PID controllers we will be discussing in quite a bit. And so the reason why these CNNs are here is just to like take some more or do some local learning. So they work with a window over your time series, and they will take some aggregate on that window, they learn it. And so that's why the combination of these two really helped well for the one on the left. But then the LSTM is probably the most important technique, I would say, here for this specific type of data. And so that's why it's the only one that's present in the one on the right.
That makes sense. I'm also curious, why did you use the Decon layer? Because I was looking at the fifth team's solution, and I just interviewed them a few hours ago. They just use Con1D as a feature. Any extra thoughts on why did you use Decon and how that was helpful?
It's a great question. I can't really accurately answer that at the moment, but I can ping back to Shoyun, who worked intensively on this one on the left, and I can post it on the forum, on the Weights and Biases forum
Thank you
today.
Sorry for so many side notes, but
no worries.
I didn't compete. I'm just trying to understand greatness from you. So that's why these stupid questions pop up.
Yeah, I'm sure your questions are very useful for the audience as well. So no worries. Interrupt me at any time you want.
Thank you.
And so the part I will be zooming in, that probably gave us about 50% of a score, or reduced the error by more than 50% in the end, which is why we have such a gap, is PID controllers. And so it's an acronym, and it stands for proportional, integral, and derivative controllers. And that sounds very complicated, but it's definitely not. You'll see it's quite simple equations, but you can kind of think of this as a controlling system that takes three pieces of information into account. And that's what anyone probably would take into account if he would make an informed decision. That's the present, which is the proportional term of it, the past, the integral term, which is typically a cumulative sum, and the derivative, which is the future, which is basically the difference of the current value and the previous value. And you can kind of, that's the gradient, so you can kind of extrapolate that to the future. And so what are these used for? Well, it's probably used in everyone's house, for example. It's to control a controllable variable in order to keep a measurable variable around a certain set point. And to draw the analogy with something that's working in your house, your temperature control in your house is probably governed by a PID controller. So there are some valves here as well that probably blast heat into the room, but of course it's not a direct effect that this heat has. It's probably there goes some time as to when the impact of this blasting of heat is actually visual. Sorry. And so
may I add another simple example?
Sure.
So when I say worked, it was a student club where we were just geeking around on evenings. That's not work, that was just hacking. But this was on a PID controller where we were trying to create a submarine. And from what I understood, it's just really helpful whenever something digital is trying to interact with something analog. So temperature is something analog and you're trying to connect it with your digital circuit. That's where PID circuits come in useful.
Yeah, that's a great analogy, actually. And so Zidmi from our team is super familiar with all of these because he has a physical engineering background. And so he probably uses or comes into contact with these on an almost daily basis. And so here we have like this inspiratory valve, and based on how much you open that, the pressure is going to change in some time or immediately. That's something that is tunable. This pressure is going to change in the lung. So this is how this PID kind of fits in. And so if we think about like how was this data generated by the organizers of the competition, well, they had this mechanical lung and there was a ventilator strapped onto that mechanical lung. And so they were either pumping up a lot of air with this ventilator or were not doing that. They simulated many trajectories of this inspiratory valve, I have to say. And then they measured the pressure on the output side. At least maybe to quickly show like how does this lung look like? Well, it's basically this. This is the one they used. So you can see like this plastic thing. That's probably where you plug in the ventilator as well. And so you can probably read out the pressure here somewhere as well. And so they made many trajectories and they read out the pressure. And so that's basically the data. And so many people believed that they just went nuts or wild with this inspiratory valve. They made some random walks or really exposed this lung to an exotic range of possible trajectories that this inspiratory valve can carry. And that would be optimal for the model because then it basically sees every sequence of possible inspiratory valve values. But as it turns out, that was not the case at all. So this entire data generating process was governed or regulated by this PID controller. So I don't know if they forgot to disable it or why it was done like that. But so the inspiratory valves and the pressures that correspond to it were basically deterministic based on the PID configuration that was used in that breath. And so, yeah, our goal or what we did was we reverted this. So we were able to switch around the arrows and basically for 66% of the data perfectly predict what the pressure would be, because if you plugged those candidate pressure values into our PID formulas, they exactly evaluated to these inspiratory valve values. And so they had to be exactly that. And so that's where I'll zoom in now. I'll quickly go through my notebook. I'll try to make it rather brief. So I probably will skip part 4 because that's a bit more technical, I would say, but it is in there. It's in this notebook, so you can definitely check up on it. And if you have any questions about it, definitely feel free to shoot out to me. Maybe before I go into that, there's like all of this code is also available on GitHub. So this will fully reproduce our solution. And from this repository, you can also go to the repos of Ricardo and Shuyun with their deep learning models in there. Okay, so let's zoom in on this PID controller matching.
Sorry, I just want to remind the audience, people watching live, there's a link in the chat on there. I'll make sure I post this link. If you're watching a recording on YouTube later, that's fine. The description will be updated with these links. If it's not, that's my fault. Just leave a comment and I'll leave the link there so that I really feel these notebooks have so many tiny details that you only learn when you're trying to go through them. So I would highly encourage you, if you're watching right now or watching later, please do read through. If not, try to re-implement this.
That's a great suggestion.
Jill,
no worries. It's a great suggestion. So here is basically, there's going to be a bit of math involved here, but it's not going to be difficult, I must say. But it's kind of essential to get to the case. But this is like the vanilla form of a PID controller. So we have an error term. Let me see, which is this epsilon, by the way, in the equation. I'm selecting it. And this is basically equal to the target minus what we measured. So again, target is the set point. That is like, what is the temperature I want in the room? Or in this case, what is the ideal pressure that I want to have in this lung? And so at any point in time, we are having a certain pressure within this lung. And so that's how we calculate this epsilon. We just subtract or measure pressure from the set point that we want to reach. And so, yeah, once we have these epsilons, we can calculate the integral with it. It's, in this case, a cumulative sum, but later we will see that it was not exactly a cumulative sum that was used in this specific data generating process. And on the third term is the derivative term. And as I said, that's basically just the epsilon of this time step minus the epsilon of the previous time step. And so then we have also these alpha, beta, and gamma. And these are just parameters of this model. These are tunable. These are just floating points. You can set them as to fit the data as good as possible. Here I just load in some data. So that's probably very boilerplate, but one thing I do want to note is, and it was really key to our solution, is that the pressure is not continuous. It is discretized. So there's only 950 unique values of this pressure, and they range from this value minus 1.89 until 46.82, and they take steps of 0.07. And so you can do this plus I times this, and then I takes the value 0 to 949, and just like that you construct all the possible pressure values. Our code is matching code, so it won't be able to match all of the data, and so it needs a baseline submission to work on. So it will try to match as much as possible, and where it finds a match, it replaces the predictions, but where it cannot find a match, it keeps the original predictions. So we'll load in a notebook here. And so let's focus on the simplest part, which is Pid controllers. And so that basically means that the integral and the derivative term are set to 0. So the beta and the gamma parameter, which was that weight that corresponded to those terms, are just equal to 0. And so if you just write out that equation, yeah, it's pretty simple. It's just alpha times epsilon. That's equal to your UN value. And so if you just write this out, like I said, the epsilon is target minus the pressure. And so you can kind of rework this equation to be in function of the pressure. And as probably maybe one have already noticed, this is completely analogous to a linear regression model. So you have one feature, the epsilon, and you have one weight, the alpha, and like that you try to predict the UN. Maybe important, we are kind of reverting the logic at the moment. So we are trying to predict UN from the pressure instead of what is given to us. UN, you're given UNs and you need to predict the pressure. But for the training set, we are given both of them because we need to train supervised models with it. So we are first working in the reverse order to get the insights, and then we'll swap it back and apply some tricks in order to apply this on the test set. And so these are indeed the parameters, or the equation in function of the pressure, but there's two parameters in this equation, the target and the alpha. And so how to find these parameters? Well, there were two ways. The easiest way is just to read the paper from the organizers. It's nicely in there in the appendix. There's about 20 possible values for alpha, and there's about 6 possible values for target, but you didn't even need that paper. You can just fit linear regression models, because that's what they are. And you can, whenever you find like a nearly perfect fit, you can kind of store the parameters of your model. And so this code snippet, which is commented out, will do exactly that. It will fit 1D models, this time from UN to pressure, as you can see here. And once it finds a fit that is like nearly perfect, it will print out the intercept or bias term of the linear regression model and the single coefficient that we learned. And so these correspond to target and alpha. But as I said, that would be the hard way, just taken from the paper. That's the easiest way, because here they are. That's the 20 possible alpha values, and here are the 6 possible pressure values. And so let's do, like, for example, a grid search with these parameters on our UN and pressure data for one single breath, the one with ID 2 in this case, and let's see how good our matching is. And so this is basically the formula I just explained. And whenever, go ahead.
So, sorry to interrupt. So just for my own understanding, we're trying to find the values for PID separately. And that is because we're trying to do matching with the same. That's why we're trying to do this grid search, because first we'd find the value for just a Pid controller, and then we'll do the same for the remaining two.
Exactly. So in the next section, so here we make an assumption that there is no integral and derivative part to our PID controller. So the beta and gamma, which were the two weights corresponding to those terms, are set to 0. And so we are first focusing on this part because it's a lot easier because you don't have that integral term. And so that's why we focused on this first. And this was actually already discovered by us very, very early in the competition. This was a post-processing technique we used to give us like a 0.005 boost, which was quite significant on the leaderboard. But little did we know that there was much, much more to discover back in those days. It was only at the end of the competition that we made a huge breakthrough. But I'll sketch some context for that. It's good that you bring it up.
Thank you. You were talking about the grid search.
Yeah, exactly. So here we're doing that grid search. So we're basically trying out all of the 120 possible combinations of these two parameters. We plug them into our formula. And once we found like a match that's like almost 0, we'll say, we'll print out the two parameters. And so this is basically it. On BREF ID 2, we have a target of 25, and this alpha parameter corresponds to 0.8. And if we then plug in these two parameters, and if we plug it in, let me scroll up. If you plug in these two parameters on the equation here on the right or the equation of the left, we are left with these two plots, or these are the results. This is the one on the left, so we go from pressure to U in, that equation, and this is the one from U in to pressure, so the equation on the right. And so they are blue and red lines, but it's a single purple line, so they're really, really matching well. As you can see, it's a perfect match. But for this, we're constantly using both pressure and U in. We're fitting a linear regression model, and only when the fit is perfect, we keep the parameters, but we don't have pressure values for the test set. So how does one go about applying this to the test set? Well, here we'll make use of that property of the pressures I discussed earlier. There are only 950 unique pressure values, and they have a fixed step in between them. So if we find two parameters, this step and this alpha, and we plug it into the formula that predicts pressure from U in, and we have a result such that all of our calculated pressure values perfectly align with those 950 possible unique values of the pressure, well, then we find a match. It's very unlikely to find for the BREF, which is the inspiratory part of the BREF, which is 30 long, to find, how do you say it, hash collisions, something like that. So it had to be a perfect match if it aligned perfectly with these 950 values.
And so, GIlles says only 950 because just to remind the audience, there are 70,000 values, and out of that, there are only 950 different values that you can work through. So
exactly, even more than 70,000. So 70,000 BREFs, and each BREF consists of 80 values. So some of them are expiratory and not used, but so we have in the range of a few millions.
Yeah.
Yeah. Okay. Yeah.
I was thinking 500,000. Maybe my math.
That's correct. That's correct. My math was off. No, 5.6 million. Sorry, 5.6 million. And then, yeah. So here we do that grid search, and so the only addition we do is here this specific error. So we calculate our predictions with that very simple equation I already discussed. Then we round the predictions to integers based on this step value. So if Pred's round contains an integer, then it was perfectly aligned with this pressure step, or this diff pressure as it is called in the code. And so that's what we want. We want Pred's round to contain integers and not floating points, or at least something close to an integer. It can contain like some decimals, 12 positions after the comma, but it had to be close to an integer. And so that's what our tune error is. So we'll basically round this to the closest integer, and then we subtract it from the actual values. And so with that, we're basically expressing how close are all these values to integers. And so if it's really, really close for all of these values to an integer, the sum is smaller than 1 e minus 6. Yeah, well, then we find a match. And so we just return the predictions and our parameters. And so we can do this again for our BREF that we just discussed when we both had pressure and U in, but now we'll just use the U in. So here I use pressure, but you can see it's not somewhere in that function. So I only use U in, as you can see in this function. And so with the U in, if you compare that to the actual pressure or predictions, well, we have this mean absolute error. And so, yeah, there is an E minus 16 in the end. Do take note of that. It's basically 0 here, just like some precision errors. And so, yeah, we can do this now for our entire training and testing set. It's a good exercise to do this on the training set first and see whether everything works. And so we do that here. And so we started off with a mean absolute error. We loaded in a submission of 0.1405. And so here we have 136 roughly. So that's a 0.004, closer actually to 0.005 boost. And so that's very significant. And you can do this on the test set as well. And actually a nice thing is that you don't need to submit the thing you did on the test set to the leaderboard to see how well it works. You can calculate your score locally as well. If you have the leaderboard score of the submission you're starting from, you can basically just calculate the mean absolute error between your new submission and the old submission. And that difference minus your old leaderboard score is going to be your new leaderboard score.
Makes sense.
So here I show this. So if we calculate the mean absolute error by the formula, we obtain this value, I believe, in the bottom. It's quite, it's irrelevant which one is which, I think. But this one is just calculating the mean or the mean differences between the new and the old submission as well. And you see those two values are match very, very well. Okay, and so that was the easier part, I would say, and so that's something we discovered rather early on in the competition, and that gave us like a nice boost on the leaderboard, but not the boost we managed to obtain in the end. The reason why we got to that boost is we got PI controllers working as well. And so in my initial formula, maybe I'll scroll to it. Oh no, it's right here. We had this, just a summation of these epsilon terms starting from value 0 up until where we are in time at this point. So it's a cumulative sum, in other words. And that is a valid way to calculate an integral, but it's not how it was exactly done in this data process. And so there are some resources online that you can check, and there are many different ways to calculate these integral terms. Often they are used to avoid numerical issues and that kind of stuff. But what we did was just trial and error with all of the possible flavors of this integral term. And after a while, we did find a match. So this integral term was not exactly a cumulative sum, but it was more of a weight decay. So it would add the newest value, but first it would kind of multiply the old values with some weight. And so there would be memory in there, but the older values their importance to the sum would dissipate over time as we go further. And so these, how many lines is it? 6, 7, 8, something like that is basically all there is to it. So this is the data generating process. You give it some pressure and it generates the U in for it. However, it needs a certain initial integral term, and that's something that is extremely hard to brute force. Luckily, there were some in there with the integral term set initially to 0, and one of them was bref ID 1. So let's just apply this little function on the pressure of bref ID 1, and what we see is this kind of match. So in blue is the original U in, and in orange is the U in hat. And we see very good matches except for the first value and these values in the end. These values in the end is just because of the expiratory phase that has already started. So we're not very interested in that. And then these first values, well, that's something we haven't been able to crack. We believe that this is just noise or random. So the first value was always random. And from there on, it wasn't that random anymore.
Makes sense.
So this, so this matching algorithm, it's really nice. But again, it takes as input the pressure. And so we kind of need to revert all of the logics again. And one very pesky thing about this function is this kind of integral term that is calculated in a for loop. So you basically need all 32 values, or you need to try 32 values, see if this for loop calculates exactly to all of your uins. And so that's a big problem. But luckily we are able to isolate this integral term. So if we take a look at how the equation looks like, this is again just a simple equation we started with. I just replaced like this summation of epsilons by just the letter I. So we have our proportional term plus an integral term, and they are multiplied by their weights. Well, we can again rework this equation to be in function of the integral term. And just like that, we are able to calculate the integral term for any point in time. And so let's get into the matching algorithm. So what we did is basic.
I would, sorry to keep interrupting you. I would just interrupt to remind the audience, I've gone through this notebook a few times before this interview, which is why I'm able to understand it so fast. If you're watching it live, please pause it if you don't understand it, because personally, I'm really slow at math. So it took me a few passes. If you don't understand it, I would encourage you to pause the video, go back, play it again. Even if you're watching that, you can pause and replay it. Or if you go through the notebook, it really clarifies a lot of things. So if you feel like all of this math jargon isn't clear to you, maybe it's just me, but for me, it took a few passes. So you're not the only one if that's for you.
Yeah, I can definitely understand that. For sure, it can indeed maybe be a bit overwhelming. So Sanyam's advice is great. Take a piece of paper and rework those equations. You'll see it is basically high school math. There's no real integrals in there. We're not analytically calculating integrals in here or something like that. So you just need that piece of paper. I can imagine it's very overwhelming here at the start. And also it often helps to just really analyze this simple function, because this is the bread and butter of our entire solution. If you can really understand this one well, you'll probably have a better understanding of how we derived all these equations as well.
So you were just going to talk about the algorithm.
Yeah, exactly. So yeah, we basically came to a whole lot of equations. We mathematically derived them. And so what we now do is, well, we have equations and they are in function of two pressure values, the P null and the P0, sorry, that's a Dunglish thing, and P1. So what we will do is we basically brute force all of these possible combinations of P0 and P1. And when we plug them into our equations and they perfectly calculate it, or perfectly calculate to our uin values, well, then we have a match. Then we know those P0 and P1 values have to be the ones at that time step. And so that's basically what we do. So we take a random P0, again, we have 950 of them. We take a random P1, we have 950 of those. So we already have 950 times 950 combinations. We also take we take possible parameter values. We have one extra parameter. In the Pid controller, we had our target and the alpha. Here, the beta is here as well, which is the weight of the integral term. And the beta term, I didn't mention that, can take the same values as the alpha term. So it's a 20 possible values for the beta as well. That can also be derived from the paper. I haven't thought about how you would find them actually on yourself. But again, they were on the paper, so it's not something to really think about. And so, yeah, that gives us another 2,400 combinations. And so you can actually multiply that with the 950 times 950. And that's the amount of possible or grid search we are doing here. So, yeah, I can't say the number. It's a big number, that's for sure. And so here are the equations I spoke about. So we plug in or P0, which you can see right here, to calculate this integral term at time step t, because we don't want to propagate our integral term from the start of the signal. We really want to calculate it at any point in time. And once we have isolated this integral term, we can calculate the next integral term, which will be based on the previous integral term. And so this is where the P1 comes into place. So this is the target minus the P1 minus the integral. That's how this weighted decay formula works. So here's another P1. But so these are just the 4 or 3 equations, because this is just a derivative of your input. It's the diff of your time steps. So these 3 equations, if they perfectly align, so if your U in hat corresponds to your U in, you have a match. Then you know P1, well, P0 is actually a risky one. I'll get into that later, but P1 for sure is a good match. P0 is in 90% of the cases also a good match. But since we're doing this for any time step in the bref anyway, you can just remove the P0s and just keep the P1s as soon as you find a match. And like that, you can kind of match the entire bref.
Makes sense.
And so here we will do this for one specific time step, and we will already fix the parameters. We knew them because we already did the entire grid search, but so we'll get into some optimization as well first, because you can't run this code. It's, like I said, 2,400 by 950 times 950. So yeah, it's a big number. And you have 70,000 brefs, so you can throw that into a multiplication as well. So yeah, it's a lot. And the time steps, another 30. But let's just focus on one time step and already fixed parameters. And let's already see how long it takes to just brute force our 2 pressure values. So 950 times 950. And as you can see, if we brute force this, this is basically the algorithm I just discussed. Then we find a match after about 3 seconds. So you have to multiply this by 2,400. And the time steps and so on to do it on one bref. And that's way too much. But as one could notice is if you just put a print in this function and you print basically this error that we're calculating, so the absolute value between your prediction and the actual UN, then you will see that this error grows linearly in function of the inner for loop. So you will see that the differences between the prints is always equal. If you subtract the one print minus its previous print, that will always give you the same value. So it's a linear line that is growing. And so when do we find a match? Well, that is indeed when this, for a specific P1 value, this evaluates to something close to 0. But if we draw this out as a linear line, maybe I have this actually in a very nice plot, then we can actually find the intersection at 0. So for what P1 value would I get a 0 error? So we can calculate this intersection. And so what we want is that this intersection occurs at an integer, because then it again would have happened in an iteration of the for loop. If it would be like this on the right, 210.5, then it would have happened in between the 210th and 211th iteration. So we would never have the match. We wouldn't be able to see it. So this is basically the first optimization. Instead of rolling out this inner for loop across 950 values, you just calculate the first 2 values, and then you draw a linear line across those 2 values. You calculate the intersection with the x-axis, and then from there on you check if it's an integer. So that speeds it up by a factor of 950 already, because that inner for loop has just been thrown away. And so if we time this, we go from 3 seconds to 10 milliseconds already. So that's already pretty nice. Another thing is that we are constantly isolating this integral terms, but actually once we calculated it once and we have it correctly, we can do the propagation. And so that's another possible optimization that is done here. Basically, if you already have a prediction in the previous time step of a match, well, then don't try to brute force this previous pressure, because it's already known we have that match, just fill it in. So that's a 950 to the power of 2 optimization if you do this. So that's already 1 million times faster, roughly. So that's quite significant. So this entire matching goes in about a millisecond now for an entire breath and for all of the time steps with, and that's important, with the parameters already filled in. So you basically have to multiply this again by 2,400 to do the grid search, but that's only 2.4 seconds. That's quite acceptable. And you can multi-process this stuff. So that's basically the order of magnitude where our code was during the competition. Okay, and so here is basically the output of our matching algorithm. So in blue are the actual pressure and in orange are matches. And as you can see, we are not able to match the first value. That will almost always be the case, but that's a detail. We found some breaths where we were able to match this first value as well, but we're not even sure as to how we were able to match those. And then here it stops matching as well, but this is the expiratory phase, so we're not really interested in this. And again,
and that also makes sense because when you're expiring air, usually you really don't need the ventilator for that. You need the ventilator just to pump air into the lungs.
Yeah, indeed. I think you can only, but maybe I'm wrong here, I'm not an expert in this, but you can only lower the pressure, right? By expiring the breath, you can't really increase it. So there's not much value of a model predicting pressure there. It's only when you're really pumping in air that you can like increase the pressure too much, and that could like explode or implode the lung maybe. So that's where it's really important to like have a control system on top of it.
Yeah, that was my thought as well.
Okay, yeah. And so yeah, our error is basically 0, and we were able to match 29 of the values in this breath. And so one very corner case of this, let me check the time actually. Well, let me just quickly briefly go over this because I see that I've been talking for quite some time already. Is when this
please feel free to continue on, but I also want to be respectful of your time. So
no worries, yeah. But so there are some corner cases. This I showed the grid of alpha. Let me quickly show it again. It's quite far up. Here it is. It's the same for beta, but so the corner case is when this alpha value takes up the value 0. So that's a very specific case. The proportional term of our model would be discarded or canceled out. And so that gave us some numerical issues. I only briefly, let me go to I only briefly discuss why it happened. So I explain here why these issues arise. But basically, in a nutshell, for any possible P null, so all of the 950 and the correct P1, we would be able to find a match. And so this P null can take any of the possible values and the matching will still work somehow. But of course, this P0 isn't the correct one. It's an arbitrary one. And so that's basically the issue we had, and I demonstrate that here. So you see these 3 points, they look like they're 0, but they're not 0. They're the minimal pressure value. They're -1 and a bit. And so, yeah, it's basically because it was the first iteration of that for loop. And like, as I said, the match is arbitrary. So it found the match there, it fills it in, but it's definitely far from correct, as you can see. And so if you would deploy this model from the previous section as is to the data, you would have some breaths in there with a mean absolute error of more than 5, and that's huge. That's huge on the leaderboard. We were working on 0.1 level, so you don't want these kind of errors in there. And we were never able to crack this fully as well. Maybe just a small note here is we were never able to fully crack the puzzle. So if someone is able to improve upon this matching algorithm or find some further insights, I would be very, very interested in hearing them. So we believe that there is much, much more to match, and that an error close to 0 could possibly be achieved. So if anyone feels like going for that and is able to achieve that, I would be very interested in hearing that. But we went for the quick and dirty solution. So as soon as we found KP zeros, we would basically clip or reset or not match all of the values at the start of a sequence. So we would just unmatch all of these bad ones basically and leave the matching away. We wouldn't try it even. So that's what we did there. It's quick and dirty. So that's one possible improvement already. You can actually try and match those. And then in the end, we also removed some noise. I'll quickly just show how the noise looks like, but it was actually discussed in the paper. Sorry, I'm hopping from one link to the other here, but I'll zoom into this paper here. And that was what it gave us, like the remaining 6%. It's section 4.2, sorry. Yeah, here it is.
No worries at all.
So they discuss two kinds of noise that they add to the data. They add boundary exploration, but that's basically a linear line added to the very beginning of the inhalation. So from time step 0 up until some time step. This time step was random and was in between these two values. They are in the appendix if you want the actual numbers. And then the other one is the triangular noise. So they would add triangles. So this could be this triangle or such a triangle. They would add that to the UN. And so we were able to actually match data with that noise in there as well. And so we reused the generate UN function I quickly discussed or briefly discussed before, where we could plug in the pressure value and get the actual UN values. And so what we did is we plug in our pressure values, we subtract that from the UN values that we are given, and what we are given or left over with is this kind of noise. And so as you can see, the noise is close to 0 for most of the time steps, but for some time steps, we can see this triangle popping up here. And so it's not a perfect triangle. That's something that still puzzles us as of today as well. So like here, this is kind of weird. It's not a nice triangle as you would expect, but on the edges of the triangle, it really fits the property of a triangle. It's on a straight line, or the slope is the same between consecutive values. And so you can really see that here. I calculate the slope, and you can see they are exactly the same. And that's the key insight we were able to use to kind of match the data. I will not go over how we did it, but I will show the impact of it. So, oh, I accidentally pressed the button of my mouse.
No
so
worries.
this was one of the breaths with noise in there. And this is the output of the algorithm I discussed up until that point in the notebook. And so you could see here in the middle, there's some values unmatched. And so we wrote two parts of the code, one to do the first half of the triangle and another part to do the second half of the triangle. One went forward and the other one went backwards. And so with the forward matching algorithm, this is the same breath. We had 9 unmatched values before. Now we have only 6 unmatched values here in the middle because of that forward matching algorithm. And then with the backward matching algorithm added on top of it, it's discussed here, and it's quite a bit of code, which is why I'm kind of skipping it for now. You can really see that we were able to match almost all of it. And so these 2 points are just where I showed that the triangle is really doing weird stuff. And that's where we're still not able to match it. And so
I also just want to point out to the audience, this is like very readable code. If at least in the world of Kaggle kernels, this is very readable. So even though we're rushing through it, that's because I also want to respect GIlles' time. This was a 90-minute session. If you literally read through every single cell, to me, like I was able to understand this, so I'm sure anyone from the audience can understand this. sorry, please continue.
No worries. It's a great suggestion again. And so like a nice thing about Kaggle here as well is that there is this comments section as well in this notebook. And I do closely follow this. So if there's anything unclear or you want more explanation about why I wrote this certain line of code, please feel free. Don't even hesitate to leave a comment and I'll gladly clear it up for you with great pleasure.
Thank you.
Yeah, and I think that kind of wraps it up. So with all of these insights combined, we were able to match like 66% of the data. And so I think we had like a model that scored close to like 0.15 on the leaderboard. And so we were able to almost perfectly match. There were some errors in there, 2/3 of that data. And so our error was reduced to 0.05 roughly. And there were only 2 teams that were able to do this, which explains the big gap in between numbers 1 and 2 and the others, and even a bigger gap in between number 1 and 2. And that's because we discussed this after the competition with Ambros, the number 2, and he didn't try to match this noise. And so this noise matching gave us the edge on the number 2. And I think that kind of wraps it up. So maybe just a small disclaimer, like this notebook is readable code and kind of, well, I try to make it as readable as possible at least. And it explains the concepts very well, but it won't be able to fully reproduce what we have done. If you want to do that, then you will have to work with this monstrosity of code that is available in the GitHub repo. But like I said, this is hacked together and added on top of each other during the competition. I guess you know how it goes sometimes. So this will fully reproduce our solution, but I wouldn't advise anyone. It will hurt your sanity a lot, I believe, to read this code. I would just go for the notebook and get the concepts from there if you want to ever try to reproduce this. And with that, I'll wrap it up and stop sharing my screen.
Thank you. This is really helpful. And also, just to point out, I was going through the other repositories, and those are models that were cleverly engineered, but those are easy to somewhat wrap your head around. This was really helpful to understand how did you reverse engineer the PID to some extent. I know there was a debate on Kaggle about this in the Kaggle circles, but I think it was really innovative. I just interviewed the 5th position team, and they also agreed this was really innovative.
Yeah, I agree. It's definitely a bit cheeky what we did. It's indeed reverse engineering. And indeed, that probably defeats a bit the usefulness of our solution to be applied to the real world. But the mistake is more in the data generating process here, right? I don't think any of the models would been able to apply to the real world because they were governed by this PID controller. If you take the PID controller away from the lung, I don't know what would happen to the models that were trained in this Kaggle competition. And there were some flaws to it fundamentally, I believe, like the fact that it was not a time series or code competition and we were given full breaths and people were actually using information from the future to predict the current pressure kind of already defeats the purpose of a real-time controller, right? If it has to wait 2 seconds in order to do something, it could already go very, very wrong.
That could be fatal.
And yeah, maybe a small note is like the typical way to achieve this is indeed thinking about this data generating process. And that's what Bayesian people do all the time. They will first think of a data generating process and what are the distributions underlying this data. And then they'll try fitting the parameters to that equation. So it's just another way of thinking about the data. I'm not going to say I'm not Bayesian at all, but it is one way to think about it.
This is incredible to learn. And also, I think the 5th position team had this incredible transformer model.
And I watched it this morning.
Thanks for joining. And it was also really fascinating to learn about how you can fit a transformer model on such a tabular and time series problem. Listening to you right now, I'm thinking maybe like because they created a 128 head transformer model, and that's like multitudes larger than what. Maybe that was just learning the PID values internally somewhere in the weights. It's hard to interpret, but that could have been a possibility as well.
Yeah, and I believe that's why the expiratory phase and all of the breath, all the information was so important to predict one single time step. Because if you look at the global shape of the breath, so the entire breath, you can kind of see what the PID parameters are. I mean, just based on what values these U-ins go in, you can kind of derive the set point from that. If you see many waves in the U-in, that means the integral term was really high there. If it's more of a flat line, there was no integral term. So yeah, I think most of the models implicitly picked up on these PID controllers. Many of the top solutions did multi-target learning. It was discussed briefly this morning as well. But so what helped really well, apparently, was just instead of only predicting pressure, also try to predict the cumulative sum of the pressure. And that's just the integral term, right? So by implicitly kind of incorporating these PID insights into the models, big achievements or boosts could have been gained on the leaderboard.
Yeah, thanks for those thoughts as well. I usually try to wrap up, and just to be respectful of your time, I'll probably just ask 1 or 2 questions. This is a common question from all Chai Time, you would know it. What's your best advice to someone just starting on their Kaggle journey?
Yeah, so I maybe gave a small tip already in the beginning, but that's probably more relevant to if you like me, if you're like too competitive, and that is to not focus on the results, but to focus on the learning experience that you're going to get from it. And I can guarantee you that you're going to get a huge learning experience from it. And you can have all kinds of backgrounds and all kinds of experience. You'll get something from Kaggle. It's always a learning experience. And then, yeah, maybe tips in general, it was, yeah, maybe try a variety of competitions in the beginning at first to see what your strengths are and what kind of data formats you really like the most. Maybe you don't like deep learning that much as I do, and then you can stay away from the computer vision and natural language competitions, or you're really into that stuff, and kudos if you are. And then you can go for these kind of competitions. But it's hard to already decide in advance just by reading some books or theory books like this is what I'm going to do. Nah, just try to get your hands dirty on each kind of problem and then really decide what am I going to specialize in. And then once in a while do go for the learning experience and take like the exotic competition that you wouldn't have picked otherwise.
Since you mentioned books and courses, any favorite resource, if you were to name just one resource where people can learn machine learning, what would you tell them?
Yeah, well, it's going to be so cliche, but yeah, Andrew Ng's courses are really good because they're not that math heavy or theory heavy. They're a great way to get a good understanding of what is in there in the machine learning domain. And to be honest, you don't even need all of those math books today to start on Kaggle, because everything is implemented in nice and easy to use libraries today. Scikit-learns and all of the other libraries make your life a lot easier. I'm not saying that you will never have to read a book, but just to get started with Kaggle, you don't have to study all of the books that are out there. You can already start today and read some books on the side. But I always say, if it comes to computer science, there's only so much that you can learn from a book, and that applies for everything. If you're starting to code, well, reading a book won't help you much. You need to actually code the stuff, and that will be the greatest learning experience.
Or if you're like me, you put them in the background and try to pretend you're smart and never really get around to
exactly.
reading them.
Or you hope that it's somehow, I don't know, through air goes into your brain or something in a subconscious level. Yeah, that's a possibility as well. Yeah.
That's very practical advice. I don't see any questions from the audience. I'll give them a minute to ask anything. In the meantime, I'll point out GIlles' Kaggle profile. You can find him on Kaggle. Shouldn't be too hard if you go to the Ventilator competition. Just look at the top of the leaderboard. Easy peasy, no worries. He's also on Twitter. I'll again post these links, but I'll zoom in so that you can see his handle. It's GILLESPDWIELE. That's his Twitter handle. You can find him on Twitter. He's also on LinkedIn, and on his Kaggle profile, you can also find his website. Any other links that you want to point the audience
No,
to?
I think you covered them all. Yeah, so I try to be quite present on social media, but those are it, the professional ones at least. I'm on Facebook, but that's more for private. So yeah, you covered it. Twitter, LinkedIn, and my website. And of course, my Kaggle profile, the most important one, to me at least.
GIlles, I'll be really honest. This really felt like I was learning from another version of Chris Diot himself. I got the opportunity to learn from him twice, and I think it was the same learning experience for me. So I speak for the audience because I'm probably the dumbest person from the audience myself. But thanks for such an educational and such a
That's a huge compliment, actually, because Chris Diot is someone I really look up to, and he's one of my idols. The way he can explain stuff, I'm still far from that, I have to say, to be honest, but it's a huge compliment. So thank you for that. And Chris, if you're ever watching, you're the man.
He's our legend. GIlles, thanks so much again for your time and for sharing your journey and your solution.
Thank you so much for having me, Sanyam, and have a good one.
Thanks everyone for joining. I'll end the live stream here.